Everyone, welcome to another Math Club Talk. Today we have our special guest, Professor Jaikumar Radhakrishnan from ICTS TIFR. Professor Radhakrishnan did his BTech in Computer Science from IIT Kharagpur and then PhD from Rutgers University under Professor Zemredi. And today he will talk about Lovász local lemma. Thank you, sir.
Thank you for coming. We'll discuss Lovász local lemma. Nothing original in what I'm saying, but this is an important probabilistic statement that somehow doesn't get discussed in usual probability courses. So I thought it would be a good opportunity to tell you about this. So let me start by motivating what this lemma is about. So you have some events. So it's a lemma about probability. Later on we will see applications in combinatorics, a couple of applications. But when I say events, I mean probabilistic events. Let me write M here. Yeah. So these are events, and you should think of them as bad events, events that we are trying to avoid. That's why it is B1 to Bn and not A1 to N. Yeah. Okay. So goal is to we want to say something about the probabilities, the dependencies among the BIs, so that we can conclude that there is at least one point in the probability space where none of the BI happen. Okay. So that's what we mean by a condition. So let me give you two examples of conditions. One is suppose the BI are independent and the probability of each BI is strictly less than. So you have some events, each of them has a probability strictly less than 1, and then we are told that the BIs are independent. Then the probability to avoid, yeah, that means all of, yes. So let me just say, so my notations are probably not what you're used to. So when I say event, I kind of, so events are supposed to be sets, but I sometimes think of them as functions. So when I say an event happens, it is as I think that BI is true. When it doesn't happen, it is false. Okay. So when I say BI bar here, it is the complement of the event. Or if you think of it as a Boolean value, true or false, which is a random value, then it is the negation of that true value. And then I put an and where you probably would have put intersection, but yeah, forgive me. Yeah. Okay. So now, because the BIs are independent, we get this product rule, and since each of these BIs had probability strictly less than 1, we can avoid. Okay, so this is something that we are familiar with. The other one is if each of these BIs has a very small probability, then clearly if there are only m of them, then if their probabilities are much smaller compared to m, then we can avoid all of them. So we can say probability of yes, and you're okay? Yeah. So yeah. The right hand side? Yeah. So if you look at the complement of this, so it is the OR of the probabilities of the BIs, 1 minus the, yeah, and the OR is the same as the union, and the probability of union is at most the sum of the probabilities. And yeah, I did a couple of steps here, but it is the union bound. Yeah. Is that okay? Yeah, you do De Morgan like a few times and it works. Is that okay? But the general spirit should be that this is your probability space and you have these events B1, B2, Bm, and so on. If the volume of each of them is strictly less than 1 over m, they together cannot have a volume of 1. So there will be some point in the probability space which is outside of all the Bs. That's all I'm trying to say. Okay. So let's look at an example where perhaps the union bound is used. Okay, so what do we want? We will have situations where we will not be able to bound the probability of the BIs by 1 over m. We have a large number of events. We are not able to bound the probability of the BIs by such a small quantity that we can just get away with union bound. Yeah. On the other hand, the events will not be independent. So we cannot just say, see, this is a very nice thing. It allows the probability of BI to be 0.999 and still it delivers the conclusion. Yeah. So, but this requires independence. We will be in an intermediate situation where probabilities are moderately small, but there is dependence between the events. But we would still like this conclusion. Okay. And the Lovász local lemma provides us a statement which allows us to make such conclusions even when we have a mixture of these two. That is, it interpolates between these two. Yeah? Interpolate in an English loose sense. Yeah. Okay. So let me look at an example. So let's say we have a hypergraph. So what is a hypergraph? There is a vertex set. And let us say the vertex set doesn't matter. And there are m edges. And this is a k uniform hypergraph. By that I mean it is a set system. It's a collection of subsets of this n element set, where each of these edges, its cardinality is k. Yeah. Now, and the number of edges is m. There are m edges, and we would like to assign red and blue to the underlying vertices, so that every hypergraph receives a red as well as a blue. Okay. So let's define m of n to be the minimum number of edges in a m of k in a k uniform hypergraph that cannot be two colored. Yeah. So suppose k was 2, just the usual graph. What is the minimum number of edges you need in a graph to make it non two colorable? It can't be colored with two colors. So no, k is 2, and I'm just counting edges. How many edges must you have in a graph so that it is not two colorable? Two color the hypergraph, meaning an assignment of colors to the underlying vertex set such that every edge or has an R and a B. Yeah. So if you have only one edge in a graph, it can always be two colored. If it has only two edges, even if those edges were touching each other, it can still be two colored. But if you have three edges, then it can't be two colored. So m of 2 is 3. Yeah. Now instead of edges, suppose I have hyper edges. Yeah. How many hyper edges what's the minimum number of hyper edges needed so that the graph cannot be colored with two colors? Okay. So this has been a famous problem, and the exact bounds for m of k in general are not known. Okay. But so here's a claim. So if you give me a k uniform hypergraph, all the edges have k vertices, but if you have fewer than 2 to the power k minus 1 edges, then there is always a way to assign colors so that every edge receives both red and blue. Is the statement clear? That's what we are trying to prove. This is the minimum that is not two colorable. That means any number smaller than that, it is two colorable, and that's what we need to prove. Okay. And the answer is assign colors randomly with uniform probability. Each vertex you put red or blue. Okay. Fix a particular edge. What's the probability I mean, long word to say it got the same color. What's the probability that a particular edge will receive all the colors the same? 1 by 2 to the power k minus 1. Either it is all reds, sorry, what were my colors? All reds and all blue. Yeah, yeah. So this is exactly equal to 2 to the power minus k, or what did you like to say? K minus 1. Yeah. So the probability that there is even one edge which is monochromatic, yeah, union bound. So what are our events now? There is one event B sub E. This is the event B, the bad event that E became monochromatic. And there are m such bad events, and we are trying to avoid those bad events. So you see the connection. Yeah, so you have some events and we are trying to avoid them, which amounts to saying that we are able to two color. Yeah. And if we do union bound, we will see that if m, the number of edges, is less than 2 to the power k minus 1, then yeah, probability of the union of the B sub E's is at most m times 1 over 2 to the k minus 1, and this will be less than 1. That means probability that even one bad event happens is strictly less than 1. So there is a point in the probability space where none of the bad events happen, and that's okay. So let us keep this as a running example. So here we use nothing, just random coloring and the fact that the probability of the union is at most the sum of the probabilities. Okay. On the other hand, even if you had many more edges than this, but if the edges were disjoint, okay, oh, by the way, k is at least 2. Huh? Yeah. So if the edges were disjoint, then there is no bound. The graph will always be two colored because each of them can be colored, or if you insist on probability, the events are independent. Yeah. And since each of them has probably, yeah, some probability, non-zero probability of being properly colored, by independence, we will get a proper coloring for the whole thing. But what about the situation? Yeah. So suppose we are not in the independent situation and we are not in the bounded situation like this, where the number of edges is small. Okay. But we are given a statement like this. Suppose each edge, by edge I mean hyper edge, of course, each edge intersects at most d other edges. Yeah. So you have a hypergraph. The total number of edges is not bounded by any reasonable number. Yeah. 2 to the k minus 1 or anything. You have a large number of edges in the hypergraph. But if you look at any one edge, the number of other edges that share a vertex with it is bounded by d. Okay. Now we would like to say that, look, inspired by this, if any edge intersects only 2 to the k other edges, 2 to the k minus 1 other edges, okay, because this edge should not really bother about edges which are far away. It should only care about what is happening to it locally. Yeah. So we would like a theorem. Yeah. So goal is a theorem of the following kind. So if each, sorry, since I have defined D, let me use D. then this hypergraph H, and ideally we would like to write an exponential in k number, okay, and what number can we write here? So this, let it be the motivating example, and now let me state the Lovász local lemma for you, and you can in your mind think about what it implies for this, but let me go here and write down the statement. So we are in this situation, B1 to Bm are bad events, and let me define obviously, yes. So you're given this event, and I'm going to define something called a dependency graph. And what's a dependency graph? So it's a graph on vertex set M, so there is one vertex for each of the events that we are considering. For each of the BIs, there is a vertex. You can think of the vertex itself as BI, doesn't matter. I'm just calling it 1 to M. Okay. And there are edges. This just happens to have some edges. This graph, yeah. So G is a dependency graph for B1 to Bm if I will explain, yeah. How should I say this? So for all S, let me explain, then I will. So you have this graph, you have this event, let's say BI, and these are the neighbors of the BI. Okay. Put them away, throw the neighbors away for the moment. Look at the remaining events. BI should be completely independent of those events. That means you tell me anything about those events, the probability of BI should not change. Okay. So technically I should have written BI is independent of any event that can be written as a Boolean combination of the events which are in the complement of its neighborhood. By neighborhood, I mean the vertex together with its neighbors. Remove them. You tell me anything about the other events. This has happened, this has not happened, this has happened, and then you ask what is the conditional probability of BI? It should still remain the same. If it was a totally independent situation, then the dependency graph, you can take it to be the empty graph, because every element is independent of every event is independent of whatever you tell me about the other events, because they are all independent totally. Okay. Yeah. What are edges? Yeah. Somebody gives us a graph. That graph has a right to be called a dependency graph if this condition holds. That's all I'm saying. I'm not giving you a recipe to construct this graph. Yeah, this is a big mistake in amateur applications of Lovász local lemma. They say that we connect two edges if they are dependent. Those events are independent. No, that's not what I'm saying. There is a graph. This graph happens to be can be called a dependency graph for this set of events if whenever you take any event in this graph, exclude its neighbors, the others don't have any influence on this event. That is the meaning of it. In this, if you want to construct a dependency graph for this, yeah, you can construct the complete graph. Okay, that's a dependency graph because, yeah, no, but we will obviously try to keep the dependency graph decent. So you take each edge here, you produce a vertex. So there is one vertex for each edge here, and you connect them if, sorry, if they intersect. Yeah, if they intersect, you connect. Now, if you take this particular edge, exclude the edges that intersect it, and you are told that I did a random coloring, this one became monochromatic, this one didn't become a monochromatic, this became, this didn't become, this became, this didn't become. And then you ask, what is the conditional probability that this became? I say, you have not yet tossed the coins for this, its probability stays the same. Okay. So basically, to construct a dependency graph for this, you can just put one vertex for each of these bad events B sub E and connect two bad events if the corresponding edges have a non-zero intersection. Now, when two edges intersect only on one vertex, are the corresponding events dependent or independent? If they intersect only on one vertex. Okay. Suppose I tell you that this has become monochromatic. What's the probability that this is monochromatic? No. This has k minus 1 more vertices. This has k minus 1 more vertices. I told you that this has become monochromatic. All right. Sorry. Yeah. So it stays the same. So notice that here, when I'm connecting these two, actually these two events are actually independent events. They are independent events in this situation. Yeah. If they had two vertices in common, then things change. But if there is only one vertex in common, they still stay independent. Nevertheless, I'm connecting them. Yeah. So that eventually I can apply Lovász local lemma. But is it clear? Yeah. Given a set of events, a particular graph will be called a dependency graph for that set of events if this statement is true. Okay. So yeah, what is written here is BI is not influenced by events far away. Okay, just keep this in mind. That is the intention of this statement. Okay. So the lemma. So suppose, yeah, so G is a dependency graph for B1 to, and maximum degree of G is, yeah, less than D, and so we are writing the sufficient condition. Yeah. So you have these bad events, but any one bad event is not connected to too many other bad events. It's bounded by some number d, and the probabilities are sufficiently adjusted. Okay, it is 1 over 4d. Yeah. Then so the union bound would have said if these probabilities are less than 1 over d, then you can avoid them. That is what our union bound argument is. Because we are not in that the total number of events is not bounded. Yeah, we lose a fudge factor of 4. Okay, so we lose 4, but then this lemma, you can say this is a souped up union bound lemma, is now applicable to situations like this. No restriction on the number of events. If any one event talks to only a small number of other events, that itself is enough to get the conclusion. Is the statement clear? Yeah, so ignore all the other things I said, just the statement of the lemma. You have events, you have a dependency graph for that set of events. Yeah. Is it clear what a dependency graph is? Yeah. This statement may not be immediately accessible, but please read it to me in this. Yeah. So I would like to prove this here, this lemma. Yeah. So this lemma appears in a paper of Tardos and Lovász. Just, I mean, so in Hungarian S is pronounced sh, SZ is pronounced s. So it is Lovász local lemma, Tardos and Lovász. Not important. Okay. So let us see. Let us revisit the independence argument, and let me say it in a very stupid way. Okay. Yeah. So, or it is always true that in this particular thing, I can always write it using conditional probability. So, what is the probability of avoiding B1 to Bm? Well, first we avoid B1. What's the probability of avoiding B1? This is the problem. Then given that we have avoided B1, what is the probability of avoiding B2? Well, the probability of B2 happening is this. So, this must be the conditional probability of avoiding B2, and then B3, then Bn. Yeah. Now, if the BIs are all known to have very small probability, yeah, then one would expect that these numbers are all small, and hence 1 minus this number is still going to be substantial, and this product should give us something greater than 0. Yeah, that's what we would like to say. Where is the catch? The catch is we are only given that each original probability is small. Yeah. But what can happen to probabilities when you condition? Sorry? They can become larger. They can become smaller, but they can also become larger. Okay. And when you look at probability of B2 given B1, yeah, given B1 bar, B1 not happening, it may be substantially bigger than the probability that the probability it had in the original probability space, not in the conditional probability space. So let me draw a picture and you will see the point of Lovász local lemma. So this is the probability space. What do you call it? Okay. And this is B1. Yeah, please don't confuse it with the edges. These are all those sample points. What do you call them? Yeah, the sample points where B1 happens. Yeah. Now you have excluded B1. So now we are in this space. Yeah, I'm doing probability in a high school language. Yeah. So you remove this. Now it could be that B2 and B2's proportion in the remaining space may be much higher than its proportion in the whole space. Yeah. At some point, you have, if you look at a particular term, you would have excluded perhaps some of the terms and you would be looking at this space, and it could be that the next event BI was jutting out way too much compared to its actual proportion in the whole space. And that is the cause for the corresponding negative term to become large. And at some point, if it just becomes the whole of the space, then it will become 1 and this term will become 0 and you will be left with nothing. We just want to make sure that it doesn't happen. Yeah. Yeah. Now, okay, I'll come. Let's look at the next second term. So whenever you write conditional probability, it has a numerator and a denominator. Again, high school probability, please forgive me. Yeah. So what is the definition of this? Yeah. How big can this get? Yeah. So what is the numerator? I mean, sorry, what did I write? What am I writing here? B2 given B1 bar. That's why nobody's answered anything. Yeah. Yeah. Okay. Now, if this number is going to become very large, yeah, or if you want to keep this number small, what do we have going for us? Well, this number, well, B2 itself had small probability. Everybody had small probability initially. So B2 intersection something is also going to be small. So let me just say this will be small, or this is bounded by probability of B2. Yeah. The trouble is, can this denominator become very big, very small? If this for this fraction to become very small, either the numerator becomes very large or the denominator becomes very small. Yeah. So can this denominator become very small? Well, this denominator is 1 minus probability of, is that okay? Yeah. If you knew that B1 was at most 1 over 4D, B1 was small, somebody is keeping the probability of B1 small, then this denominator is not going to become too big, meaning this probability is going to shoot up, but shoot up by some small factor. Yeah. In particular, if we can ensure that all these numbers were less than half, this would be at most 2 times the probability of. So if the denominator can be kept at least half, we can somehow argue that at every stage the denominator will be at least half. Then these numbers can be bounded by this. Is this okay? Yeah. Now, keep this picture in mind. I will, where should I go? Oh, here. So I'll erase this. Let us understand a general situation. Yeah. So we are trying to analyze. Yeah. Probability of bi given and j equals 1 to I minus 1 bj bar. This will be one of those negative terms there, and we would like to keep this small. Yeah. Let us do it in this picture. So there was a b1, there was a b2, there was a b3, and there was maybe b. I mean, they could of course overlap, but I'm just drawing what they bring new. Yeah, 7, and there is bi minus 1 here. Okay. And now there is this event bi, and we would like to claim that bi's conditional probability. Now, what is condition? Which is the conditional space now? The space that bi occupies in proportion to this is not too large, is what we are trying to prove. So that 1 minus that is still something decent. Okay. Now, what could cause bi's conditional probability to fall down? Okay. Now, we know that even though this is j equals 1 to I minus 1, most of the bj's don't have any influence on bi because of the statement. The maximum degree is d. There are only d bad fellows here. If I had conditioned, so this conditioning can be thought of as first conditioning over the faraway events and then conditioning over the nearby events. There is this event bi. It has d events perhaps which are nearby. Out of them, God knows how many are included in this. D could be 20, but only 7 of them could have been before I. Okay, don't worry. Let us say there are at most d of them. There are nearby events, only d of them, and then the remaining, what is it? I minus 1 minus d of them are far away events. Okay, so I will write down the formula, the mathematical expression, but I would like you to kind of anticipate what I am going to do. First, let us condition. Yeah, so step 1. Condition on far away events. You understand what I mean by that? Look at all the things in the range, or let me just call it T is all those events j such that j is less than or equal to I minus 1 and j is not related to I in the dependency graph. Or should I say ji does not belong to the dependency. That's what I mean by far away events. Yeah. So let us condition on, just let's exclude the far away events. So we get a picture like this. Yes. And I'm only drawing the far away events. Yeah. So these are bi, bj, where j is strictly okay. Yeah. So j belongs to T. Yeah. let us condition, we also have to condition against these. We'll come to that. But the good thing is, now if we look at this probability space, what is the probability of BI here? Whatever it was, it has not gained. We have been able to condition off a good number of events without taking any damage to the probability of BI. So BI after conditioning is still, its probability is the original probability. Let me call it PI. So this probability, let us call it PI, yeah, just so that I don't have to write it. So even in this conditioned space, this fellow has probability only PI. Yeah. But we are not interested in the probability of BI after excluding only the friendly events which are far away. There are also nasty events which are in your neighborhood. Okay. So they are going to eat up. Yes. Yeah. But in this space, how much are they eating up? The probability of Bj conditioned on the faraway events. What is this number? In proportion to this, it is the probability of Bj conditioned on faraway events. Faraway events with respect to Bi. Yes. But we were interested in a conditioning which had size I minus 1. These fellows are now wondering what their probability becomes when conditioned on fewer things, perhaps I minus 1 of fewer than I minus 2 of them. Do the oldest trick. Let us assume by induction that conditioning never increases your probability by more than a factor 2. Hypothesis. Or let me just write it. So let me write it in English. Conditioning does not increase the probability by a factor more than 2. And what I mean by that is probability of Bi given anything you condition on and some subset L, yeah, which doesn't include I, of course, yeah. Suppose this is my induction hypothesis. That is, take any event, exclude some events, yeah, and then ask how big does your probability become. That is the sort of trouble we were worried about. My claim is that suppose this is true, okay, then is this an induction hypothesis that can support itself? Yeah. Now we were doing this, right? So this probability, when we were first excluding this, the numerator, wherever our numerator, I should do it properly. Yeah. For every L not including I, that is our claim. Yeah. But let us, but for the moment, let us, I will, yeah, let me go on, but you'll see why, what is moving the whole thing, then we will see, then we will do the rest. Yeah. Suppose I were to prove that this holds, yeah, this was true before and I want to prove it now. That means I want to prove that this probability of Bi given this is going to be small, okay, yeah. So what happens to the numerator? The numerator is at most nothing happened. The old calculation, the numerator was something intersect some other event. So its probability cannot be more than the original event to begin with. Okay, so numerator is always safe. Denominator, we are computing the denominator and numerator in this conditioned space where we have conditioned out the t. Yeah. So in the denominator, we will have an expression of the form yes, we are conditioning on the far away events not happening, and then we are asking what is the probability that even the nearby events did not happen. Yes. Now, somehow the number of such events here is how many? How many are there? Sorry, what did I write? Everything is messed up. J. Yeah. What is the probability of, we are looking at, yeah, this probability, but we are excluding this part. How big could these have become? Okay. But how many are there? How many such events are there in the complement of T? How many nearby events does any event have? At most D. So this object here has at most D. And when the numbers are small, number of events are small, we should bravely apply union bound. And now we do this union bound with the hypothesis, with 2bi. Yes. So this is at least 1 minus D of them. Each of them has taken a hit of factor 2 in their probability, but their probability used to be so the numerator grows no more than, did not increase, and the denominator reduced, but did not reduce to anything less than half, which means we have, using the induction hypothesis, we have completed the induction. I have no, okay, so let me start again. So what is our induction hypothesis? Sorry, so did you see the magic? Yeah, yeah. So now it's just a question of writing everything nicely. So what will be our hypothesis? The hypothesis is, where did I write the hypothesis? This one? Yeah, this was the hypothesis in some English, but, and this is true for all L where I does not belong to L. Yeah, and we will prove this statement by induction on size of L. When L was 1, L was 0, no conditioning, yeah, the probability remained the same, it was only B1. When L was 1, that was this calculation, yeah. When L is some general thing, you split L into T and L minus T. T, who are T? Among L, who are the far away guys? And L minus T, L, yeah, set minus, those are nearby things among. First condition on far away, numerator did not change. But these BJs might jump up. Say that our original probability was small, but now you are conditioning on L minus T. what happened to our probability? You say, but we have taken care of you in the induction hypothesis because L minus T is, yeah, if T was the entire L, that means this particular event was independent of all of them. Then it is just Pi. So we can assume that there is at least one dependent guy among the things that we are conditioning on. And then we apply induction, say that, look, yeah, you had some complicated relationship with the other events, but that relationship is not going to increase your probability by a factor more than 2. They have to accept it. It was induction hypothesis. Then we do this calculation. Numerator bounded by Pi, denominator. So hence, probability of Bi given and Bj bar, J belongs to L, where L doesn't include I, is at, well, if L included I, it would be probably be 0. But yeah. No, no. No, yeah, so let me write it down again. I do want this, but let me explain. I'll go up there, yeah. I'm saying that this particular space that I'm talking about here, when I've excluded T, this is the conditional space. Yeah, so maybe I should have written T or something here. T is the guys who are far away. What is my T? Far away guys, sorry. Yeah, sorry. Is that? Let me explain. Let us write it down properly. Yeah. So we are trying to prove this hypothesis. Okay. Base case is true. Okay. Let us do it. So now let me write down the left hand side. Probability of Bi given and J belongs to L. Yeah. Bj bar. Is this okay? Yeah. Good. Yeah. Now we define T. I'm writing it again. All those J belonging to L such that Ij is that okay? Sorry. Yeah, these are far away events. Okay. So now I'm going to write this as numerator and denominator, but my numerators and denominators both will have conditioning on. See, once you write this math, it becomes terribly confusing, but you will help me. This is numerator. If I have conditioned on these things not happening, then we are asking what is the probability of Bi? Yeah. So this event conditioned on this. Yeah. And the denominator, among these, there were the T's and there were the t complements. The t's are already being conditioned up, so it is just the remaining. Yeah. So what should I write? Yeah. Is it okay? Yeah. I mean, now, how do we analyze the numerator? We say that it is an intersection of two events. So the probability, it can be no more than the probability of bi conditioned on these. But these don't affect bi. So numerator is definitely bounded by pi. Is everybody okay now? Yeah. And denominator is working out. Yeah. Denominator, I'm probably just insulting you by saying this once more. Denominator, now we apply 1 minus sum of the probabilities of the bj's. Yeah. But bj's, it's not plain old bj like we had in that b2 example. It is bj conditioned on these. But we have given enough muscle to our hypothesis that even with conditioning it can rise at most by a factor 2. So denominator will be at least 1 minus summation j belonging to L minus far away events, probability. Should I write, or would you just allow me to write 2 times pj? Yes. Yeah. And since pj's originally were bounded by 1 over 4d, and this has at most d terms, this quantity is at least half, and we have proved that this pi divided by half gives you 2 times pi, and our hypothesis has been established even for sets of larger size L, sets L of larger size. Is that okay? Yeah. That's the end of the proof of Lovász local limit. Yeah. Okay. Now, so obviously some calculations can be tightened. Yeah. So let me do this. Let me write down the general form. This is how it appeared in the Erdős Lovász paper with this factor 4, etc. But the general form. So you see, different events might have different number of neighbors. So maybe events which have lots of neighbors, their probability needs to be bounded more. Events that are kind of not related to other events, maybe they can have high probability. So maybe one can write a more general theorem. Okay. So let me write down one more general theorem. Where should I do this? Yeah. So, okay. So you see that theorem. Let me just replace, and then you will tell me the hypothesis. By the way, here I just used the union bound. Yeah. But we started off by replacing the avoiding union bound by writing this expression. Yeah. While I write down the lemma, can you think if that could have been used here? Okay. So let me write down the new version of the lemma. So the events are the same, the dependency graph is the same, but suppose there exists x1 scalars, x1, x2, xm, let us say in the range 0 to 1, such that probability of, oh, by the way, so once we have proved the induction hypothesis, what is the final probability? What can we say about the probability of I'm saying that top expression, what can I write now? Sorry? Yeah, 1 minus 2p1. Just, I know there is no 1 minus 2p1. This was just 1 minus p1. Yeah, the first few terms were probably doing even better, but since all these pi's are so small, 1 over 4d, all these numbers are, yeah, these numbers are positive, and so the product is positive. Yeah, okay. So suppose the probability of bi is less than, so yeah, the theorem will look like this. Okay. Now I just want to make sure that you understood. So how will I modify this proof? Yeah. So you see, yeah. Suppose I replace this by xi. Okay. So I'm saying that I want to redo the proof of Lovász local lemma here, and I want you to think, I want you to tell me that it's all okay. So my claim is that I'm going to now work with the induction hypothesis xi. What are xi's? Xi's are those special numbers that have been given to us. Okay. Then, okay, I mean, hypothesis is there, but what about the proof? Yeah. So the numerator, this numerator, sorry, where was my numerator? This would be bounded by this. What would happen to the denominator? Here I said 1 minus the number of events times probabilities. Yeah. But here I have no control on how many events are there in the neighborhood. Somehow the xi's are mediating the effect. Yeah. But notice that what did we want to exclude? We wanted to compute this probability. Yeah. But if the induction hypothesis tells us that each bj, even though its probability was this small, after conditioning it never becomes more than this. Excluding this factor means raising the probability. It never becomes more than xj. Then this I can compute directly by product, 1 minus xi, 1 minus xj, 1 minus xj. Yes. So what would the numerator look like? Numerator will be this expression. Denominators will be, and you'll get back your xi. Okay. It's all set up so that the proof works elegantly. Okay. But I'm not going to do this proof. I'm assuming that the moment I have told you this xi, you will manipulate and get the answer somehow. Okay. Is that okay? So this is the general form of the Lovász local lemma. And then what is the final expression? Here, what should I write? Equivalent of this. Yeah. Okay. So maybe I'll write down what its consequence was for this hypergraph thing which I have erased. Yeah. So, yeah. So if H is a K uniform hypergraph where each edge, okay, sorry, So let us decide what to write here. Then H is, sorry, at most D others. 1 second. And D is not too large, and that we will fill up here. Then H is 2 color. Okay. So let us try to apply this statement or that statement to conclude a statement like this, which is what we started. Yeah, we only need local conditions for colorability is what we wanted to play. Okay. Now see, suppose it is actually the dependency graph has degree D. Suppose the dependency graph has degree D. Actually, then you can set each of these xi's to be 1 over D plus 1. See, we would like to get the best possible Lovász local lemma. Yeah, which means we would like to allow these BIs to have as high a probability as possible and still get the conclusion. Is that clear? I mean, if the BIs had very small probability, okay, that is going for you. We would like a lemma which allows the BIs to have very high probability. So what should you choose these xi's to be so that this quantity is maximum? This is something you can do better than me. And it turns out that if you set xi to be 1 over D plus 1, then the right hand side looks like 1 over D plus 1 times D over D plus 1 to the power or something like that. Sorry, is everything? What am I doing? Yeah, to the power D, 1 over D plus 1, D over D plus 1 to the power D or something like that. Yeah, and this is like 1 over E. Yeah. Yeah. So the condition 4, this number 4, yeah, that can be replaced by E if you did these things more carefully, and instead of D you write D plus 1. Okay. So instead of this, so instead of this, if you write 1 over 4 D plus 1, then this would still be true. Yeah. Then this conclusion can still be obtained. Yeah. So in our case, the degree, yeah. So if it is the case that D plus 1 is less than what was the probability of BI? 2 to the k minus 1. Sorry, divided by E or multiplied. No, there's something wrong. Where did this E go? Sorry. No, so this had become E, right? So we want this probability to be D plus 1. Yeah. So we have a k uniform graph and we allow each edge to intersect an exponentially many other edges, not quite 2 to the k minus 1 that we might have dreamt of from union bound, yeah, but a good fraction. And it turns out that one can ask, is this constant E here optimal, yeah, for Lovász local lemma? That is, can someone come and change this E to some number less than 1? Turns out no, there are events where every event is dependent in the dependency graph sense. Every dependency graph has only d neighbors, but still, if you increase your probability to be beyond this, there is no point in the probability space where all bad events are excluded. Okay, so this constant E is optimal. Yeah, at least for large d. For small d, something better is known, but if d becomes large, this E is essentially optimal. You cannot improve this E. Okay, good. So should we take a 5-minute break and then come back for half an hour, or should I just continue? There is no tea outside. Yeah, anything is fine. I'll just continue. Is that okay? Then you can take a break while I erase the board, whatever break means. Sorry, yeah. So what am I mean, those of you who want to leave can leave also. That's the big advantage of a break. Yeah. So what am I going to do now in the next half an hour? Usually such events arise in algorithms. Yeah. So you want to build a randomized algorithm to find such object. For example, you are given a graph which has a large number of edges. Yeah, huge number of edges, but every edge intersects only a few other edges. Theorem sort of promises, Lovász local lemma promises that there is a two color. Find the two color. There is one. Okay. One thing is, try every possibility, one of them will work. Yeah. And that would be a brute force algorithm and that won't be efficient. Okay. So you see, the final conclusion of the algorithm, the Lovász local lemma is 1 minus some small numbers and a large number of them. Okay. Now, when you are trying to do a randomized algorithm where things have reasonable probability, say probability 1 over n, then you can say, oh, try n times. The chances are constant that by that time you will find it. But if your original probability itself is something which is exponentially small, you just repeatedly try randomly, the number of trials you will need, I mean, you toss a coin which has probability p, how long do you need to get a success? 1 over p. So if you're, so this is one of those probabilistic methods or probabilistic methods for ascertaining the existence of something where it says the probabilistic method works, but it works with very small probability. It just says the probability is greater than 0. Yeah. But then this usual trick of just repeat it and wait till it happens is not going to work. Okay. But nevertheless, in this case, there is a beautiful algorithm. Yeah. Actually, the algorithm is completely natural, but it has a beautiful analysis, and I wanted to show you that. Okay. So what is the theorem I am going to write? So I have to be, the original Lovász local lemma was stated in a general form of a probability space. So let me just say that there are okay. Let me just, so this assumption is still there. So let me write down that assumption. Probability of BI So we are in a situation where we are being a little more precise about the events BI. So you have tossed some coins or some random variables x1 to xn. They are being tossed independently, generated independently. Now B1 looks at only the coin toss 7, coin toss 9 and coin toss 13, and it either happens or not, doesn't happen based on the outcomes, those outcomes. B2 looks at some others. Yeah, each event looks at some of the primitive outcomes and its value is completely determined by them. Okay. Now, in the sense of dependency graph, just as we built the dependency graph for the hypergraph case, we will, if you have some event and another event, this event is influenced by some set of variables, this event is influenced by some other set of variables, and those variables have nothing in common, then those events will be independent. Yeah, so that is why we declare two events to be adjacent if their influencers have something in common. Okay, so now if you take an event and exclude all the events which have a common influencer, common variable, if you remove them, the remaining events, they might have complicated dependencies among themselves. Okay, but they are not in any way going to influence this. Okay, which is sort of the situation that we had in the graph coloring place. There we were tossing a coin for each vertex of the graph. So there is one xi for each vertex of the graph which takes the value red or blue. Okay, and a particular edge depends only on the colors of the vertices that it contains. Whether it becomes monochromatic or not doesn't depend on some vertex that it doesn't contain. So that is the situation. And suppose this is true, so Lovász local lemma is applicable, but we would like an algorithm. Yeah. So then the following algorithm finds a realization, a valid realization, let's say, yeah, for x1 to xn in time, in expected time, so these numbers xi 1 minus xi, yeah, which in the general form of Lovász local lemma seem to be set up just because of some engineering concerns, yeah, because some cancellations should nicely happen, etc. They actually have a meaning. They have an algorithmic meaning. They control the expected running time of this algorithm. Which algorithm? I am going to tell you. So now I am going to erase all this. It's a little unfortunate that I sort of use the same exercise. Yeah, let me, I don't know if I'll be careful enough, but yeah. Let me just say, let us say there were k variables, k underlying variables. So what do I mean by this? This is a particular realization of these random variables. That means pick Z1, Z2, Zk from this product distribution. Yeah, pick one instance. Yeah. So in our case, these are random variables, and this one is R, B, R, 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 B, R, B. Some realization comes up. Okay. This will be the current realization. Our goal is in the end to produce a realization so that when we plug that realization, then all the events, all the BIs will get excluded. Yeah, we want such a realization. It exists because the lemma is true. Okay, how do we find it? Yeah, so step one, just pick a random realization. Now, if all BI are excluded under this Z bar is this thing, then stop. Okay. Step 3. Yeah. So you should think about it like this. So here were some events. Again, this is not the probability space. These are the underlying random variables. Yeah. X1, X2, X5, X7. And they all lit up. Some of them are off, some of them are on if they were binary random variables, but they could be some other random variables. Some of them take various values. Then we ask this event, are you excluded? It says I'm excluded, no problem. Ask this, ask. If there is even one event that is not excluded, that means it fires up, says that I am true. Yeah. Then what do we do? Yeah, let Bi be the first event not excluded. That means it is true. Yeah, that event has happened. Then what should we do? We want an assignment where that fellow is excluded. This assignment seems to have excluded a good number of other guys, but unfortunately Bi, it has not excluded. So what should we do? Resample only the variables of Bi. That's the algorithm. So there were some events. Each event had small probability, but there were so many of them that whenever we toss the coins, some bad event or the other was happening. Okay. So we tossed the coins once. There was a bad event Bi that happened. We looked at B1, B2, B3, B9 was the first event that happened. We don't go further. Go to B9 and try to set things right. Why? We just take its variables, the variables that were influencing it, and say that, look, this is a bad setting of these variables. Let us reset those variables according to the original distribution of each of the xi's independently. Yeah. And now again ask. It could be that now that B9 has, maybe B9 again is bad. Okay, again resample. Okay. But it could be that B9 got sorted out, but B2, which earlier was quite fine, shared some common variables with B9, and now it starts firing up. Then go sort it. somebody else, like you, it's like, on a bed you try to make some things nice, you do it here, something pops up there. Okay, yeah, this can keep happening, but the theorem says it will settle down. After this much time, no bad event will survive. Why? Because this hypothesis was true. We have to make use of this hypothesis. Yeah, events had small enough probabilities originally. We are not guaranteeing that immediately everything will be right. Things went bad, we sorted them out, something else which was good became bad, blah, 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 and eventually we will converge to a perfect solution. That means a valid realization of Z1 to Z. Is this clear? Is the statement clear? Yeah. So let us run this algorithm. And let us record which events required resampling. Okay. So initially there was an assignment. Then there was some resampling and one more assignment came up. And this went on for a long time. And we want to know that it doesn't, we want to prove that it doesn't go on for too long. So let us write down under this realization which events were resampled here. Okay. So they were A1, A2, A1. And we want to know how long this can continue. And we want to say that it cannot continue so much. Yeah. And our claim, the claim that we are trying to prove is that each BI is not going to be resampled. Yeah. So number of resamplings of any BI, yes. What do I mean by this? This is the number of resamplings of BI means how many times this AI was the same as AJ was the same as BI. This quantity and then linearity of expectation takes over. Okay. Okay. So the only thing we need to prove is focus on one BI and ask how many times does it get does it get resampled. Okay. Sorry, there is a term whose name I have forgotten, so let me look it up. So I'm going to draw a tree, and this will be the tree of now when these things got resampled, it's a very simple thing. Everything is elementary probability. So don't worry. I mean, yeah. So the reason something got resampled, it has, yes. So we should ask, why did it get resampled? Okay. So before drawing the witness tree, let me just look at this matrix of realizations. So when I'm thinking of this algorithm, yeah, so initially there was, this was, let me call it alpha 1 0, alpha 2 0, alpha k 0. So what are these? I sampled x1 to xk and put down the values here. Okay, I sampled them once, put down the value. Then I resampled completely independently and got alpha 1 1, alpha 2 1, alpha k 1, alpha 1 2, alpha 2 2, alpha k 2, and so on. Yeah. So right in the beginning, I just repeatedly sampled completely independently and filled up this table. Okay, with some events which are nodes which have resampled, they have no children to blame, they just blame bad luck, because in Z0 itself they came out bad. So let me repeat myself. So yeah, let me repeat what I just said. So we are going to build, so yeah, so we have fixed a particular T, yeah, and we are asking, does this event, why is it that BI, suppose we had this, what's it called, this transcript, and we look at AT, and AT happens to be BI, and we are trying to understand how could it be that AT was equal to BI. Okay. So we believe that there is a cascade of causes that resulted in BI happening at the Tth step. We want to record it as a tree, and we will then analyze that tree. Okay. So look at this. So BT, yeah. So we start with BI. Then for j equals t minus 1, t minus 2, so on till 1, if aj shares a variable with some event in the tree, attach it to the lowest such event. Okay. So is it clear? Yeah. So BI, look at the previous one. This is AT minus 1. Now we ask AT minus 1, do your variables, AT minus 1 might have been B17. Okay. Does B17 share a variable with BI? If it doesn't share a variable, BI says, look, yeah, I mean, something happened to you, but I cannot blame you because you did not resample the variables that are hurting me here, that caused this. So we go. Finally, we find somewhere B12 is written. And it turns out that B12 and BI share a variable. So we stick. Okay. We find that B12 is here, and we find another AI which shares a variable with B12 and BI, and we look closely and we find that that is BI itself. That is, there was a moment when BI happened, maybe it got sorted out, but later on we tried to correct B12 and that must have BI again. Okay, so in that case doesn't matter, since B12 is sharing that variable with Bi, we write Bi. We go here. B4. Now B4 doesn't share any variables with Bi and B12, but it happens to share a variable with Bi. Sorry, no, sorry, what I missed. Doesn't happen to share. Okay, let me just, it was a bad idea to do this, but anyway. So suppose there was a B4. Yeah. Now this B4 doesn't share a variable with Bi, but happens to share a variable with. Then we stick it here. Okay. And this way we keep looking at the tree. Yeah. The point is that the events that we write at a given level, they don't share variables at all. Because if this event and this event both shared a variable, when we were sticking this, we should have stuck it under this, not there. Is that clear? Yes. So any node, if you take, its children don't share variables at all in this tree. Okay. This particular tree is called the witness tree for time step t. So the question was, if B4 shared a variable with Bi but not B12, even if it shared a variable with B12, we go to the lowest, attach it to the lowest such event. Yeah. In this tree, B4 shares a variable with somebody in the tree. Among the nodes in the tree, find the lowest one and attach it. Okay. It could be that there was a B7 here. B7 and B12 don't share any variables. B4 shares a variable with both B12 and B7. Too bad. Yeah. We stick it at the lowest. Okay. So whenever there is a Bi appears at time t, there is a tree that is formed. Yeah. And the question is, what is the probability of this tree appearing? Yeah. So this Bi, why did it blame B12 and B7 eventually? Because it had sampled some variables Yeah, so I don't have the time to write everything actually. Yeah, but assume that these variables which I have put crosses on are the variables that Bi had observed. Those were the variables that it depended on, and it didn't like them. Yeah, so it wanted to resample. So for each of them, it asks, who was the last guy who set me? And the last guys are this, yeah, last meaning from this, whom should it blame? Yeah, this resampling, and maybe there were some variables which actually nobody resampled. Yeah, they were there, but they combined with the actions performed for sorting these out eventually caused this. Okay, in this picture that won't be true because there is a Bi already, but don't worry. Yeah. So whenever you have a particular event, there is a set of variables that it is involved in. Okay. Now let us just look at this B12. Yeah. B12, maybe it was responsible for this resampling. There is a patch of variables that got resampled when B12 was. Out of them, there was this variable. Yeah. So when B12 was being resampled, these variables of B12 were in this configuration, and these variables got resampled, and instead of this value appeared, instead of this value appeared, instead of this value appeared. Some of the variables, some other value appeared, but BI has nothing to do with it, so it doesn't care. You understand? For each element in this tree, there is a little disjoint patch of variables that caused it, and these are all disjoint. Yes. So the probability of this tree happening, that this tree arises, is the product of the probabilities of the events that appear on the tree. So let me write this statement down. This might need some thinking. It is because the moment you tell me the tree, I know which variable in this matrix is actually responsible for that resampling of BI. Yeah, you look at this tree, you say, oh, B12 and B7, oh, all these bottom guys were using the basic variables. Then we say who resampled, and you'll be able to reconstruct and decide just based on the tree, not on the position T. Once you tell me the tree, I know what caused, which variables caused BI to happen, okay, for which it was resampled. Okay, good. So suppose that is true, and so I'll take 5 more minutes and try to finish the argument, because there is a beautiful punchline at the end. Don't go away. So so maybe I should say things a little better. We have this what is the word I used? Transcript. Okay, the paper calls it a log, and I know that in a mathematics lecture, if I say log, it's going to confuse everybody. So I've called it a transcript. But once you have this transcript, yeah, look at any node, any event, you can build its witness tree. We can say, why did this event need to be resampled? Oh, well, it blames somebody, they blame somebody, they blame somebody, they don't have anybody to blame. This always happens. Yeah. So for every particular resampling in this transcript, there is a tree associated with it. Yeah. The trees might have different number of nodes. Yeah. The resampling, this one and this one might have the same number of nodes, because perhaps these involved some variables and this involved totally different variables. Yeah. Whatever. But whenever you have a resampling, there is a particular tree whose root is that event. Okay. So fix a tree T with BI probability that appears, yeah, while processing the transcript. So processing is this business of building the tree. This has nothing to do with the algorithm. This is an algorithm used as an intermediate step in the analysis. Okay. Yeah. So I'm sorry, since I have to rush, I am not defining anything, but I hope you understand. So probability that T appears is equal to the product for all vertices that appear in tau, probability of the label of the vertex. What's the label of a vertex? Label of the vertex is the event that you write there. Yeah. So our goal is to sum over all tau with BI as root, product V belonging to tau So we want to know among, if the BI appears 3 times, the 3 trees will be different. Is it clear? Because this tree will actually have that BI in it. Yeah. So the trees will all be different. So we just need to count how many trees, how many witness trees with BI as root appear. Okay. And just by linearity of expectation, if you know that the probability that a particular tree appears is this quantity, you believe that, then by linearity of expectation, the number of trees, yeah, is this, and our goal is to show that this quantity is bounded by, yeah. Okay, so if something is not clear, don't worry. I mean, if you go and sort it out at home, it will be fine. Find my, okay. Let's look at a particular tree. BI appears in the root. Then it has some children. These children will be events that are neighbors in the dependency graph because they share variables. Yeah. So let me give some concrete numbers here. B7, B5, B4. Yeah. And this has some children. This has some children. This has some children. And so, yeah, let's stop here. This is our tree now. And we want to compute this quantity and sum it up over all trees. Yeah. Just pay attention. What does this number, bound on this number, look like? Xi times 1 minus xj, sorry, product j, where j is, okay, and suppose here this was BL, then this will be XL times product j, which is neighbor of L, 1 minus xj. Yeah, all these nasty numbers are sitting here, but very soon they will kind of, I mean, yeah, you will be thankful that these are the numbers that are sitting here. Okay, so let's see. Here is what I do. Look at BI. Some of its neighbors in the dependency graph appear as children. Some of its neighbors don't appear as children. Okay, add dummy nodes for those BS, BR. These are J's which appear in this product but didn't happen to appear as children in this tree. Yeah, put them here. Make a new tree. Yeah, so take your original tree and attach dummy nodes whenever a child that was expected, that is a neighbor, does not appear. Yeah, so we wanted to initially compute the product of these numbers. I'm just going to do a manipulation to compute this number. Okay, actually compute this sum. So I'm just saying first modify, add dummy nodes, dummy leaves to the tree. Now this BI, among the dummy nodes, you also add BI, yeah, so including BI itself. Okay, please ask if something is not clear. So every node, if it has a BL, if BL does not appear as a child already, when would BL appear as a child? If BL was sampled, resampled, it did not sort BL out, you had to resample again. Yeah, but if BL did not appear as a child, you attach BL as a leaf. Yeah, okay. Now there are some numbers, the dummy nodes don't have any numbers on them. Only the internal nodes, the circular nodes have numbers on them, and we are supposed to sum over all trees of those numbers. Okay, good. Here is what I am going to do. This xi I am going to pull out. I am supposed to take the product of this. So this xi I pull out. This xi I have written here. Okay. All the other numbers I am supposed to write. So all such trees will have a little xi on top. So I pull them out. Okay. I would also like a 1 minus xi here, which is not there because these are the neighbors. Yeah. So I multiply by 1 minus xi. And so I divide by 1 minus xi. Okay. So now I am supposed to sum over all trees of these new values that I have put on the trees and show that that quantity is at most 1. Because I have written xi over 1 minus xi, I just want to show that this is at most 1. Okay. Just watch. There is a product of 1 minus xi's, you just push it down. Yeah. So sorry, why did I? Sorry, I have pulled the xi out. Maybe I'll have to deal with that. I'm a little confused about that, but don't worry about this. So all these 1 minus xi's, I just move them to their corresponding children. These, yeah, if bi appeared here, then you move this 1 minus xi to this. If bi appeared as a honest to God original child, you move that 1 minus xi. The 1 minus xi's, you just move them down. Yeah, okay. So in the first step, nothing is left. Actually, if you don't mind, I would like xi to remain here and just leaving a 1. Okay, yeah, xi here. Okay. Then I go to this node. So this, whenever a dummy node, it has received its 1 minus xi, it shuts up. No further processing. Okay. This B7, what did it have? It just received a 1 minus x7 from its root. It used to have its own x7 and 1 minus xj's for its neighbors. Yes. So this B7, x7 it keeps, 1 minus x7s it pushes down. Pushes down, pushes down. Everybody does this. Traverse this tree in a breadth first search fashion. Whenever you are at a node, keep only the xi factor, 1 minus xi factor, give it down. Whom do you give it to? It may be a dummy node, which you created because it was not there, or it might have been a child with that name. In that case, it gets 1 minus xi. So it could be that this 1 minus xi, which was given here, was given to some bi which appeared here. It passed it on, passed it on. In the end, it will settle down. Now, what do our numbers look like? We have a tree in which, yeah, maybe I should have pulled the xi out, doesn't matter. Yeah. bi is here. B7, was it B7? B7 has an x7. This was B5 has an x5. B4 has an x4. Every internal node has its x value sitting on it. x11, x22, maybe x5 again. Yeah. But whenever you have a dummy node, it has a 1 minus xj sitting on it. Look at this. You have a tree xi 754, x11, x2, x3. These are the numbers. The dummy nodes have this. Notice. You have seen this before. Imagine a process. Okay, so this is a wordle. Yeah, can you guess? So there are two words. If I say that, you will see it. Yeah, letters of the English alphabet. Just guess. Sorry? No, any letter. Just guess. Any letter of the English alphabet. Sorry, C doesn't appear here. E doesn't appear here. Starts. Huh? A. Yeah, go ahead. Huh? P doesn't appear here. Sorry? I doesn't appear here. E doesn't. S. Then? No. T. Three and this. If those funny numbers xi's were not thought of as some funny number Lovász created, but actually probabilities of those events, then this was a tree produced by a Galton-Watson process. So this sum that we are, after pulling out this, yeah, is just, I mean, if I left the xi there, yeah, so it is, I start with a bi, so bi is fixed, and now I let loose the Galton-Watson process, that whenever a node is there, it regenerates all its children, but now with probabilities that corresponding xi, and I want to sum over all trees of the numbers that appear here. That is exactly the probability that that particular tree appears in the Galton-Watson process. Yeah, so maybe I should just, for the camera. Oh, sorry, yeah. So that probability, this mess, after pulling out the xi and this, must be bounded by 1. Okay, and our theorem is complete. Is that okay? Yeah. So once again, just summarizing. I'm sorry for taking so much time. What did we do? We had events which were bad events. Typically, a situation where union bound is applied to exclude the bad event. Union bound is usually like there are some bad occurrences. We try to. This happens all over probability, but sometimes we exclude them because we have independence. Sometimes we just use the union bound. But there are situations where neither of them is applicable very easily because the probability of the events that we have is too large to apply union bound just like, without thinking. On the other hand, we don't have independence. But we have limited independence in the sense of the dependency graph. Yeah. If you exclude some small d number events, the rest have no influence on this event. In such a situation, we can apply the Lovász local lemma, yeah. But there is this souped up version of Lovász local lemma where these numbers 1 minus xi's etc. were there, but it is the same idea, yeah. Only the neighbors are set and their variables are something. Okay, and we proved the lemma because we had this inspiration to write down the induction hypothesis that if you take any event, exclude some events, its probability can rise, because that is what hurts us when we do the calculation without paying attention to independence. But it cannot rise too much, at most a factor 2. If it is xi, it goes from a number less than xi to xi. Okay, that is how that proof went. And then in the end, you write 1 minus product of xi or 1 minus product of 2 pi's, whatever you want. Okay, that is how that proof went. But that proof was only an existence argument. Where is the algorithm? In special situations where the events arise out of variables, different events listen to different variables, okay, and two events might have dependency only if they are talking to a common variable. They are being influenced by a common variable. In such a situation, an algorithm can be written down, and the algorithm is resample, resample, resample till you succeed. Okay, but don't resample the whole input. Resample only that part of the input that part of the realization Z which is causing you trouble. And how does it cause trouble? Some event Bi which was meant to be excluded didn't get excluded, so you resample it. Okay, that is the algorithm, and its running time is bounded by the sum of these quantities. Why? Examine the transcript. For each occurrence of an event in the transcript, think a little deeply. Why would that event happen there? It is because of a witness tree. And then notice that the witness tree uses variables, that patch of variables which are all different, so you can write product. This product looks very similar to Galton-Watson with a little shifting of factors. Yeah, this 1 minus xi here means the process died there. That event did not, that child was attempted to be born and it didn't. Okay, so that was those 1 minus xi's. These xj's here is when you made that experiment and that child was born. Yeah, so it is exactly the same as the Galton-Watson process. Yeah, and the sum of all the trees that ever appear in the Galton-Watson process is at most 1, because that's what probability theory says. Thank you very much. Yeah, you should go eat. Yeah. Questions? So there is more to this. I don't know how. I mean, there is a. Should I just? Yeah. So there is a book of Alon and Spencer on the probabilistic method. It does not, I think, have this analysis of the algorithm. This analysis of the algorithm is from the original Moser Tardos paper. There are also other. There are many applications of Lovász local lemma. I meant to do one more to arithmetic progressions. That is, can you color integers using a small number of colors so that there are no long arithmetic progressions with small common difference. Yeah, the point is that when you have two arithmetic progressions, they typically will not intersect in much. Yeah, because the common difference of one has to be multiple of the other. So the degree d in the dependency graph stays bounded. Actually, yeah, so in this case you have to be a little careful, but yeah, there are many such applications about existence of a coloring, existence of a combinatorial object, where there are many local conditions. Local conditions are easily met, but then there are dependencies, and you use the local lemma to deal with the dependencies. Yeah, some other time. Thank you. Okay, you should go. Yeah, question. Yes.
Is there a way to optimize the initial realization?
Yeah, so I don't really know. I mean, yes, there might be. So the original choices of the exercise you could probably choose based on this. But in the end, the hypothesis has to be met that the probability of the event should be less than this. How to choose those xi's so that that is true, I'm not sure. But the other thing is, this just says expectation. Can you show something with like high probability, the concentration? So there are, the original paper of Moser and Tardos also talks about that. That is, if you relax these conditions that I had by epsilon, then you can actually say that with high probability it will stop here. An important area of research still is that finally you run this Moser-Tardos algorithm and it provides you a realization. Does it sample uniformly from the set of all realizations which are valid? This is some process which is guaranteed to give a realization, but maybe it has a favorite realization which it always gives. But there are many other realizations. Okay, so it turns out that it doesn't give exactly uniform on the set of all realizations, but it is not off by too much. Okay, so such works also exist. So yeah. So that was another thing I want to say for this coloring. It is true. So suppose I give you so I had a theorem about bipartite graphs here, and I had an E, and I was debating whether it's in the numerator or denominator. Yeah. Now, what did that control? That controlled only the neighboring events. Now, and it says that take any finite graph, finite hypergraph, where a hyperedge doesn't intersect with more than that many, then it has a valid color. What if your graph is infinite? Yeah, compactness. So, turns out that such theorems, if you prove for every finite number, then it also is true for infinite. So, give me any infinite graph, any number, I mean, there is only one, yeah, infinite graph where each edge intersects only with 2 to the k divided by e, many other edges. What is k? K is the number of vertices in the edge. But the number of edges can be, it has a valid 2 coloring. Okay. So, this goes, so I don't know in your combinatorics course, have you been, no, so there is something called Koenig's lemma. Every finitely branching infinite tree, sorry, you have 5 minutes, let me tell you how that works, how finite can be translated to infinite. Let me just do it for countable, yeah, countably infinite. So, you have this hypergraph and it has edges E1, E2, so on, yeah, and it has the condition, yeah. So, let us just say every finite subgraph of H is 2 colorable. This implies that H is 2 colorable. This is a general theorem. In any graph, if every finite subgraph is 2 colorable, every finite induced subgraph of it is 2 colorable, then the whole graph itself is 2 colorable. K colorable, R colorable, doesn't matter, yeah. And the reason is the following. Let us write down E1, E2 and so on, yeah. I build a tree. So, right in the beginning, yeah, so maybe E1, E2 and so on, yeah. Now, look at the vertices of E1, yeah. How many of them are there? K. So, how many possible colorings can be there for those K vertices? Sorry? Yeah, 2 to the power K. There are 2 to the power K colorings. And how many of them are bad? No, those are good. No, sorry. How many of them are bad? Either all red, all blue. Yeah. So, 2 of them are bad, but the others are all good. Yes. Okay. Now, look at E2. E1 was this hyperedge. E2 brought some more vertices. Let us say S more vertices. Then, each of these colorings now can be extended to a coloring of E1 union E2 in how many ways? We have already colored E1. This is one particular coloring of vertices of E1. Now, E2 has come, there are S more vertices, 2 power S. So, this degree would be 2 to the power K. Now, this way you can build this infinite tree. At every node, there will be at most, the new edge would have brought at most K new vertices. Those can be colored in 2 to the K. The previous ones have already been colored. If you have taken a particular path, that means the previous ones have already been colored. Now you are asking this. And what does this hypothesis say? that on every level there is at least one node which is a good coloring for E1 to E7. That is the, yeah, at least one of them is a good coloring. Here all but two are a good coloring. Yeah, but if you have a good coloring, what about its parent? It is a good coloring for E1 to E7. That means its parent must have been a good coloring for E1 to E6, because if E1 to E6 already bombed, then E7 can't work. Yeah. So if you look at these shaded nodes, there are shaded nodes at every level of the tree, because every finite subgraph has a valid color. So if you just look at the trees consisting of these shaded nodes, it is a finitely branching infinite tree. Any finitely branching infinite tree must have an infinite path. This is called Koenig's lemma. Yeah, every finitely branching infinite tree must have an infinite path, which means there is a way to color the new vertices and new vertices and new vertices forever and never violate. Okay, now this is getting into slightly set theory type of argument. Yeah, so you can inductively define and whatever use principle of induction, saying that you can, so look at the vertices of E1, they can be colored, then that coloring can be extended, can be extended, can be extended, and extended forever, and by the end, all the EIs, each EI, its vertices get exhausted at the ith step. Yeah. Once we have passed through a shaded there, if I cannot complain about some later action, yeah, because its decision has been frozen. Yeah. So yeah. So if you have this, you have this. That's all I wanted to say. And this is called compactness. It is your usual, what's called Tikhonov's theorem. Yeah. So you can write this as with some product topology and the compactness of that what product of compact space is compact. I don't even know what it means. Yeah. That theorem you can plug in, yeah, if you have enough muscle. But for I remember it like this, that any finitely branching infinite tree has an infinite path. Question, sorry. Yeah. Any more?
So thanks to our speaker.